Okay, I think it's time. Hello, everybody. So thank you very much for joining EPFL AIP joint seminar. I'm Ichiro Takeuchi, team leader of data-driven biomedical science team. I chaired today's seminar. I'm very pleased to introduce Professor Michael Unser. He is a professor and the director of EPFL's biomedical imaging group. His main research area is biomedical image processing. He has a strong interest in sampling theories, multi-solution algorithm, wavelets, and the use of splines for image processing. He is the author of over 150 published journal papers in these areas and is one of the ISI highly cited authors in engineering. So thank you very much for your talk, Professor Michael Unser. I would like to ask the audience that if you have a question, please type it in the Q&A box. And after the professor's talk, I will read out and start the question and answer time. Okay, thank you very much. Okay, please start.
Okay, so hello everyone. And first of all, I'd like really to thank the organizers for the invitation, also for the presentation. And so what I want to tell you today is about new representative theorems for inverse problems in machine learning. And in some sense, inverse problems is the domain where I'm coming, like imaging, so which, you know, I'm sort of involved in research in biomedical imaging. And of course, we are very much relying on machine learning those days. And what I want to convey to you actually that there's a big connection between those areas of investigation and that you can have cross-fertilization. So maybe just to tell you a little about my background, and so that's the general also problem of biomedical imaging. So what you have here, you have an object. So for example, here a map of fluorophores in a cell. That you're looking at this through a microscope, and so what you're getting is blurred and noisy measurement. And so what you would like to do from the measurements, try to recover the original object. And so since you know of the physics, so you have an underlying model that you can write here as a linear model with a matrix H. And of course, you have also measurement noise. So how do we usually go to solve this problem? So we will write it as an optimization problem using regularization. And so you have here, you're trying here to find a solution S. So that's this desired object that you try to recover. You know the physics, it's H, you have the measurements Y. So you're trying to construct a solution that is close to the measurement, but often the problem is ill-posed. That's the reason why you put a regularization and so put a penalty on some norm, L, for example, being the gradient and P being 1 or 2. Okay, so this is sort of the classical framework also for compressed sensing. Now, if you look at supervised learning, actually what you have an inverse problem as well. But I mean, one difficulty here, because it's in infinite dimension. So the very basic supervised learning problem, so you are given some data points. So let's say features X and Y, some desired output. And now the goal is really to find a function F that maps Rn into R. And so the training, you would like to do it such that if you put like a certain pattern vector X into F, that it will provide you with the output. So this is a sort of classical regression problem. And of course, it's completely ill-posed because you have finite data and you're looking for a function that lives in a continuum. It's so very basic, many years ago. So, I mean, Poggio, Gerosi, others proposed to use regularization theory. And so to define some kind of smoothness functional like L, for example, being the Laplacian. And so what you are trying to do then is to actually solve this problem. So you would like to find a function such that the prediction is pretty good, like within the level of noise. And to deal with indetermination, now you will look for the function that minimizes this energy here in a certain Hilbert space, and which can be a reproducing kernel Hilbert space. And that's where actually comes in the very rich theory of reproducing kernel Hilbert spaces. And so you can show actually if H here is a so-called reproducing kernel Hilbert space, then you can find that in fact the solution leads to kernel estimators. And so that has been a very important topic in classical machine learning. Now let's just to set up the scene. I mean, this is the classical stuff, okay? But of course, there's the modern stuff with neural networks. So let's look at a very simple problem. So let's say you have some data points like that. You're in 1D, and you want to learn the map here, y equal fx. So what solution would you propose? So here I run, you know, several algorithms, and these are the different outputs that come. Now, I'd like first to show you those two, because they are the result of classical kernel, you know, Gaussian kernel machine learning. So using two different Hilbert spaces, but so where you can adjust the width of the Gaussian. And so here it doesn't work so well, especially where you're missing data. So either you get a drop, or otherwise you do over smoothing. And then here are some other solutions using you know, like other functionals than Gaussian kernels. And now what is the commonality between those solutions? Actually, I have like different regularization terms here, and now they all produce actually a function that is continuous piecewise linear. So they all produce splines, but they have different regularization. And now if you throw a neural network at the problem, you also get something that is continuous piecewise linear, so a ReLU network. And actually, my two preferred solutions are those, okay? And that's what I'm going to develop in the talk. And in fact, they are very much connected. Okay, so in fact, here's the outline of the talk. So first, I want to give you some foundations. And so we're going to talk about Banach spaces. And I will present to you this unifying representer theorem. So that's what's announced in the talk. And then I will show you how this theorem actually allows you to crank out a broad category of algorithms here, and how it also relates to deep neural networks and actually allows us also to optimize deep neural networks. And so now underlying here, I have the abstract notion of a Banach space. And so what is a Banach space? It's simply a vector space, but equipped with a norm. But now what's important, the notion of Banach space is really also that the space needs to be complete. That is, if you have a sequence of elements that is a Cauchy sequence of elements in that space, then that the limit points should also be in the space. Now, okay, Banach space are immensely general, because first of all, I mean, it covers, of course, linear algebra, so the case of finite dimensional vectors. It also covers linear spaces of functions, so functions like f that I'm trying to find in the supervised learning problem. They also cover linear spaces of vector-valued functions. So if you, of course, in machine learning, you need to do multi-valued functions. But it also covers something more general, actually, spaces of linear functionals. And actually, if you want to be super general here, it actually covers even here, it is like going a linear functional going from a Banach space into R. And here you can even be very general. So linear functions that go from one Banach space into another one are also from a Banach space. So the thing is amazingly general and covers almost anything you need. Now, if you have a Banach space, there's also the so-called dual of a Banach space. and so if I have this Banach space X, the dual, I represent with a prime. And this is just the space of linear functionals acting on the elements of the parent Banach space, so F. And so what is a linear functional is just a rule that for every function will give you, will output a real number. And the rule should be continuous in X. So if you change vary the input. And so X prime, so the dual is also a Banach space if you equip it with the so-called dual norm, which has this definition. So it's just the supremum, you know, over all possible inner products or duality products here, normalized by the norm of F here, and you're looking for the supremum over all F. Now, actually, if you look at the definition of the dual norm, it's very obvious that actually what you have here is that actually this X here is this X prime norm will be greater than this thing here. Okay, so because we're taking the supremum, and then actually what it gives you is this inequality here, which is true for any dual pair of Banach spaces, and in some sense it's the generalization of the Cauchy-Schwarz inequality. And now to be concrete, for example, if X is one of the LP spaces, now you have a conjugate exponent P prime such that this is true, and then actually these P primes here are the duals of LP primes are the dual of the LP Banach spaces, and in that case, actually this inequality reduces to the well-known Holder inequality. But this inequality is true for any Banach space, not only LP spaces. And actually this relates to the so-called risk conjugates. And so now if you have Hilbert spaces, I mean, this is an older theory, but that's well known, and it's in some sense equivalent to Cauchy-Schwarz. Actually, now if you have a Hilbert space in this dual, then you have this inequality, is the same as the duality inequality that I just show you here. But what is more interesting here, you have a mapping that's called the risk conjugates, so that takes an element of H and produces a dual element which is in the dual space H prime, such that actually if you do inner product between, or duality product between U and U star is actually equal to this, and so that gives you the squared norm of the unique the initial element. Now the properties of this duality map or the risk conjugate is that in fact if you take U and consider the U star, the U star will have exactly the same norm as the U, but I mean the same value of the dual norm, and then actually the duality, this risk map is linear, but it is invertible. So if you apply the inverse to U, actually this operator here, it's precisely the risk map, but the inverse of the risk map gives you the duality map, and then it's invertible. So if you do the conjugate of U star, you get back to U, and it's linear and also is an isometry. Okay, so this is very classical, and actually this also maps, I mean, it's consistent with the space being reflexive. Now there's a generalization of this duality map. If you have now, or the risk map now for any dual pair of Banach space, then you can also, given some F, you can define some element F star, and you will call those two guys a conjugate pair if now, as in the Hilbert case, now we have the norms that are equal, but you also have a sharp duality bound. Okay, so that now the duality product between F star and F is actually equal to the product of the norm, which in that case is actually the squared norm of F. And then now what's different is that given a certain F in a Banach space, there's not necessarily a unique conjugate, but there can be a whole family of conjugates. And so that is called the duality map of F. And there's always at least one of those guys. And in some cases, actually, this duality mapping is single valued. And this is the case when the Banach space is strictly convex. And then we have a duality operator that will take an element in X and produce actually this F star, which in this case is unique. Now, the properties of the duality mapping. So, as I said, every element of a Banach space has at least one conjugate. Now, the duality map, the set of conjugates of a given point is convex and weak closed. And now, what I said, the other important part, that actually it's single valued if the Banach space is strictly convex. And so this just means that actually the norm associated with this Banach space is strictly convex. And here's the definition of strict convexity. And for example, all the LPs are for you know, P between 1 and infinite, but the borders not included are strictly convex. And now, in particular, also you have the case of reflexive, when actually the double dual of X is equal to X. And in this case, you're also automatically strictly convex. Okay, now here comes the representer theorem, and I call it the Christmas theorem because you know, it was Christmas 2018, and you know, my wife wanted me to pack the presents, but I was insisting on improving this theorem, and I actually just managed to prove it in time so that I could finish wrapping up the gifts for the kids. But anyway, so here's the representer theorem. So now if you want to minimize this functional here, okay, so what you have, F is in a given Banach space, and so you have data points and some functional acting on F, so you want somehow this to be consistent with your data, and you are putting a functional here. It's some nonlinear functions applied to the norm in that Hilbert space, in this Banach space here. And so E here is just any strictly convex loss functional, and phi is some arbitrary strictly increasing function. Okay, so what can we say about this problem? So the first thing we can say that this problem has always a solution, but not necessarily unique. But the very important thing we can say that actually there's lots of structure in the solution, and that now all the guys that are in the solution set are Banach conjugates, so X prime X conjugates of a common mu zero that actually lives in the space that's spanned by those mu's here. And so if I want to make a drawing here, so you have a single mu zero, which is something you need to determine. But if you need to know this guy, then actually the solution set here are all Banach conjugates of this single guy here. And then now the solution now depends on the type of space. Now, if you have a Hilbert space, now it's super nice because then actually the solution all live in a linear manifold, and that is spanned by some functions, but those functions are just actually the Banach conjugates of the new M, so which are the guys here that are acting on F. And so this gives you a very nice structure. So now, if X prime, on the other hand, is strictly convex space, then actually you also have a unique solution, and you have a kind of similar representation, but now, okay, you have a single point of solution, but now this single point is nonlinearly related to this new via this Banach duality map, and so then you have a nonlinear manifold of solution. And now the third case is super interesting because now if X prime is not strictly convex, in this case the solution is not unique, but it will have extreme points. And now we can show that the extreme points of the solution set, which are those points on the boundary here, they can all be a linear combination of a small set of atoms. And now these atoms here are extreme points of the unit ball in the given Banach space. Okay, so now maybe to make that a little more concrete, so you know, so if you have a convex set, usually usually every convex set will have some extreme points, and they're just like points where that are not included within a segment, in a segment that are boundaries of segments. Okay, that would be that you can draw within your convex set. And now the thing here that if you have extreme points, you can actually represent S as the convex hull of the extreme points. Now, what about extreme points? So if we look, for example, at LP spaces, so here you have LP balls in 2 dimensions, and so this is like the locus of all the points that are at the distance one from the center. Now, what can we say? For example, for L infinite, the extreme points are those 4 points here in red, and so then this let's say the square then is just the convex hull of those 4 extreme points. Now the other interesting case is L1, where actually the extreme points are those purple guys, which are inherently sparse. So they're like Kronecker guys with a 1-on-1 coordinate and 0 otherwise. And otherwise, for the other LP, actually all points here are extreme. So the result then is not so interesting. So then you go to the second part of the theorem. And so if you have strictly convex Banach space, actually all points on this unit ball are extreme points. Okay, so now let's crank out a few results. And I will show you how this will take us from classical to modern regularization-based technique. So first of all, let's do classical learning. Okay, and then here we have to select the Hilbert space, and we select a Hilbert space that is a reproducing kernel Hilbert space. And what does this mean? It just means that the Diracs, which are the sampling functionals, are actually element of the dual space. And this is completely equivalent to being reproducing kernel Hilbert space. And now, if you now look at the conjugate of those Diracs, what you get is actually the so-called reproducing kernel. Now, if you look at the learning problem, so in the Hilbert space, so you're looking at minimizing that subject to a penalty on this Hilbertian norm. And so here we're exactly in the case of the theorem, so strictly convex, additive here functional. And so we can actually apply the theorem. So in this case, X is actually the conjugate of the Hilbert space. X prime is actually the double dual, so it's our Hilbert space. The news are the Diracs. The loss is additive. And so the news being the Dirac, this is very specific to machine learning. And in this case, actually, this duality map is actually an operator here whose kernel is exactly the reproducing kernel of the Hilbert space. And now what you get here is the basis function. They will just be the image of the Diracs, okay, through this RIS map. And this gives you kernel because it will just extract here those values of the kernel. And so at the end of the day, what you get is just that your solution here is a linear combination of kernels. And so the kernels, okay, now the kernel here has 2 indices, but so one is taking as the output variable, and the other one is fixed and correspond to the location of your data points. Now, now how does that match with regularization theory? For example, if you take quadratic Tikhonov regularization here, you can choose a certain operator, for example, the Laplacian, or you know, some actually not the Laplacian. You rather want some that is invertible, and it needs to be shift invariant. So that is, this would be an operator that has a frequency response, And then actually what you have is this functional picture here that somehow here you're using a L2 norm, but after application of the operator L, and so you have this mapping between L2 and your Hilbert space H, and then you can also determine actually the dual space H prime, which is given here. And now if you look at this picture, actually you see that in fact this duality map is the map that where you go from this H prime to H, which means applying the inverse of the operator, but the conjugate, the inverse operator. And now, since those are convolution operators, you can actually represent these operators in the Fourier domain, and you can actually get the impulse response of this operator by inverse Fourier transformation. And this is what you get here. And then, in fact, if you just put that into the theorem, you get this linear combination of shifted kernels on the data point. So that's very, very classical machine learning. Now, this also relates to splines. For splines here, what we use as an energy is the L2 norm of the derivative of the function. And so there we have this regularization function. The operator is the derivative. Now there's one difficulty here is because you have a non-empty null space, which is actually formed of constants. And then what you can do, in principle, this makes it harder, but what you can do, you can actually factor out the null space and have this direct sum topology of the space over which you're optimizing. And now if you factor out the null space, you have a unique inverse, and that you can actually, in this case, you need to invert this operator here. So it's actually D2, this second derivative. If you go in the Fourier domain, you can, so the derivative, the inverse of the second derivative, so it will give you 1 over, so omega square. And that actually, this impulse response is just 1/2 of absolute value of x. And now if you put that in the theorem, now what you have to add also is a null space component, and otherwise a linear combination of those kernels. And this gives you the very classical smoothing spline solution, which goes back to 1960. So it's very, very classical. And of course, it gives you a piecewise linear solution. Now, what we want to do now is maybe do something a little better, okay? We were using L2 norms, and we all know that maybe we prefer sparse solutions. So the idea now is to put the L1 norm instead of a L2 norm, to choose the same operator as before, that be shift invariant and invertible. And so there, in principle, we have this mapping between L1 and the space in which we're optimizing. Unfortunately, this doesn't work because it doesn't fit the theorem. And why is actually because we cannot find a space X such that L1 would be the dual of that space. And actually, the fundamental reason is also that if you write the optimization problem with L1 norm, actually it doesn't have a solution. You have a limit point, but it's just outside the space. So let's try again. And actually, the right way to do it is to, of course, use the proper norm. And so, for example, L1 in finite dimension, you can define it as the dual of L infinity. In infinite dimension, it doesn't work, but there's a so-called space C0, which is the space of continuous bounded function that decay at infinite. That is actually a little smaller than L1, L infinite, but is the right space for our purpose. And actually, the dual of that space is the space of measures, the so-called radon measures, which are associated with this norm. And now what you just need to think that this space of radon measures is a superset of L1. And so in particular, if you're in L1, this radon norm here, the M norm, is the same as the L1 norm, but the space of M is larger than L1. And in particular, now we have the extreme points of M, they are Dirac's, which is super important for our theory. So now if we go back and now choose this M norm instead of the L1 norm, then we can do all this thing, have the frequency response, the extreme point we know, and we can apply the theorem, actually the third case of the theorem, and we find actually that the solution of this optimization problem now with the M norm, there are a sum of kernels, but now the very interesting thing is that there are few kernels and that the kernels do not no longer live on the data points. And so that gives us a much better representation and adaptive kernels. Then what we can do, we can actually do the same with splines, also use the M norm of the second derivative. Now here, again, there's a problem because we have a non-empty null space, but again, we can use a direct sum separation of the space, and there the second derivative has a explicit inverse, and then we can crank out this theorem that tells us actually the solution now. Okay, now it becomes interesting, okay, because it's a sum of a linear term plus those guys, and now you will recognize that those are ReLU, like in neural networks, okay, so one-sided power functions, and that actually gives you a piecewise linear solution, but with very few knots, and this will be a sum of ReLU, and we even have an algorithm that will, although the solution is not necessarily unique, we can find the sparsest one, and in many cases, the sparsest solution is unique. Okay, and now maybe to show you that in the background, this is not necessarily so simple, okay, because here you have points, okay, so you would like to interpolate them maybe linearly. This is the classical solution, just connect the dots, and this is the spline solution, 1966. Now, if with this M norm, you can also play that game, and you will find this. Okay, so it's very interesting because it's much sparser. It has a single knot, and it goes through the points here. It's not necessarily trivial that you will find this solution. Now you can also do Lipschitz splines because I think being sort of stable is an important consideration also in learning. So if we put the L infinite norm, then we can also, this is also a case of a non-strictly convex Banach space. Again, we have a null space. We can do a direct sum decomposition of the space, and then D again has a unique inverse if you factor out the space. I mean, in this case, also what's important, we need to know the extreme points of L infinite, and now they're not Diracs. I mean, they are functions that are either 1 or -1. You know, that can alternate in wild fashion. But now, if I integrate those extreme points, now I get those U guys, which actually are piecewise linear with slopes plus or -1. And then I get a solution like that. That's also piecewise linear, but possibly many more jumps, but that can be characterized explicitly. And we also have an algorithm that can give you the sparsest solution, because this kind of solution is not necessarily unique of that optimization problem. So anyways, the main point that I want to make, that, you know, all those solutions, every solution that I've shown to you, they're actually special cases of the representer theorem, except maybe the neural network. Okay, but what's amazing in the neural network, it looks so much the same as what comes out of this L1 spline techniques. And so that's what I like to tell you in the reminder of the talk, actually, how this relates to neural network. So now some background. Neural network, people like a lot ReLU. It's sort of arose as a result of Darwinian evolution. It seems to work very well. Gives you often state-of-the-art performance. But people have also early on noted that if you put ReLU activation in the neural network, actually what you produce is actually a map that is continuous piecewise linear, exactly like, you know, what I was discussing with the representative theorem. And also that, in fact, those ReLU network can be interpreted as splines. So now if you look at the deep forward neural network, so you have neurons like this. So what you have now, you have an activation function for each neuron. And then you know the arrows that connect the neurons actually represent affine transform linear weights, and eventually you can also have a bias here, and then you have a nonlinear step at the level of the neuron. So if you look at the neural network, essentially you can compose affine pointwise nonlinearity, affine pointwise nonlinearity, etc. And this produces a neural network. Now, the relation with splines, and for example, in 1D, okay, here is a continuous piecewise linear function, and it is in fact a non-uniform linear spline. So it is a function of that form. So you can partition the domain in intervals here. And so those taus here are the knots of the spline. And you will say that the function f is a linear splines with knots on the tau k if now the function is linear within every one of those intervals. But the second less obvious property is actually the function should also be continuous. Okay, so at the joining point, and that's the difficult part with the splines. But now if you write your spline as a sum of ReLU, this continuity is automatically satisfied. Now, this notion you can also develop in higher dimension. In higher dimension, what you need, you need to partition your domain in polytopes, so convex polytopes, and then you will say that the function is continuous piecewise linear with a certain partition here. If for any one of those regions it has an affine form here, which is given here. And now the difficult part now is making the affine pieces continuous at the junction of those polytopes. And now, if you want the vector value continuous piecewise linear function, of course, every one of those components must be continuous piecewise linear. Now, there's something really fantastic with those continuous piecewise linear function because they form an algebra. So every linear combination of those guys is continuous piecewise linear, which is obvious. But what is a little less obvious and super powerful, that if you compose them like in a neural network, the composition of any two continuous piecewise linear function with compatible domain and range is actually continuous piecewise linear. It's actually relatively easy to show because continuity is a property that is preserved through composition. And now affine is also a property that's preserved through composition. So now if you put the two things together, you get the result. And now if you do max or min pooling, that actually also preserves continuous piecewise linear. So what are the implications for neural networks? So if you take a ReLU network, which is a composition of those guys, so every neuron, if you put a ReLU activation, is obviously continuous piecewise linear. Now, and now if you put every layer where you have a part here that's just affine, and then followed by this continuous piecewise linear functions, you know, by composition, it's also continuous piecewise linear. And also by composition, the whole thing is continuous piecewise linear. And actually the same, this thing still holds true if you use max pooling, and also if you use more complicated activation functions, provided they are continuous piecewise linear. And so I like to say that a deep neural network with ReLU is actually a high dimensional spline, okay? And it is a true statement. Okay, so how can we relate that to the theory? So first we can make a very nice relation between, you know, in dimension one. So limit behavior of univariate shallow ReLU networks. And so if you look at the, you know, shallow network in one dimension, you can write it like that. So using those ReLU functions. And now, okay, since there's a determination of those W and V, usually one puts weight decay. And now what's fantastic, and this can be proven. So now if you look at the solution of that problem, okay, which is what the neural network training solves, is actually equivalent to the solution of that problem, which I just showed you before, which was using this M-norm regularization. So now if you what's amazing, if you use now a minimization problem in Banach space, and I never talked about neural networks, actually the solution of that problem is a neural network. Okay, the extreme point of the neural network. And that was, observed by Savares and Pai. Now, it turns out that this is also generalizable in higher dimensions if you use actually the Radon transform. And so, I mean, here I have to go a little fast, but the problem is in high dimension, somehow you want, to get activation, somehow you need to project in one dimension. And so that can be done using the Radon transform of computer tomography. And there's a so-called filtered back projection algorithm, okay, that allows you to reconstruct a function from its Radon transform. And so there's a certain operator there. And now if you look at the, this shallow network, but in higher dimension, again with weight decay regularization, now you can show that is actually solution of this functional optimization problem, where now I'm using again a Banach space and a norm that involves the Laplacian and the Radon transform, and then it's a M norm in Radon. So which I think is relatively amazing, because in this problem I never talked about neural network. I just talk about optimization in function spaces, and out comes actually the structure of a neural network. Now, what we can do is even a little more now. Let's be a little bolder, okay? So who told you that ReLU is good? Okay, of course we tried and it works really well, but can't we possibly do better than using ReLU? And so a crazy idea, why don't we also try to optimize the activations in the neural network? Okay, so here's my neural network. I told you it was a composition of affine followed by pointwise nonlinearity. Now let's be crazy. Let's also optimize the pointwise nonlinearity, okay? So let's train everything. F, okay, the weights and also the nonlinearity. Now, of course, you tell me it's, it's ill-posed because nonlinearities are functions, so they have infinite degrees of freedom. But now we can actually rely on functional optimization. and so we want to use a regularization on the nonlinearity that should not penalize simple solution like identity, linear scaling, should impose differentiability because we want to be able to apply backpropagation, and also favor a simple CPWL because, I mean, those work so well in practice. And so therefore, we actually choose to optimize the M norm of the second derivative of the activation. And then you can actually define a corresponding Banach space that actually fits exactly the theorem that I presented to you. And then you get actually this theorem here, which is what I call representative theorem for deep neural networks. So you choose just your favorite, cost function. Okay, so that can be anything here, like in the deep neural network framework, some regularization that you put on the weights, whatever you want, and you put now, you will also optimize the nonlinearities, but those will be optimized by taking their second order total variation, so the M norm of the second derivative. And now the amazing thing is that we can prove that the solution of that problem actually ends up with having nonlinearities that are actually splines. They are themselves splines, not just one ReLU, but a sum of ReLUs. And now what's the outcome of the theorem? So that every neuron now has a certain number of nodes. We don't know how many. Okay, this is the outcome of the optimization with some location and also some expansion coefficient. And all this is data dependent, automatically adjusted during training. And now the other fantastic thing, there's a link with L1 optimization theory, because actually the weights to put in front of the neurons, I mean, this penalty here corresponds to the L1 norm of the weights that you are putting here in front of those values. Okay, and actually then global optimalities are achieved with spline activation. So in particular ReLU. So ReLU is a particular case of this theorem. Okay, let's not forget standard regression, okay, because you know that's Gauss, okay. So if we let the regularization that we apply to this total variation, the lambda, go to infinite, actually this kind of architecture will produce a linear regression. And then actually state-of-the-art parametric ReLU. So here people have proposed, instead of putting just one ReLU, putting a ReLU, you know, with a piece of a straight line. This is also part of the theorem, and you can also put more knots. And so people had proposed that before, and it usually works a little better than just having one ReLU. And so in principle now this architecture that comes out of the theorem looks to be interesting. But now I mean, there are some issues here, so we need to adjust one more parameter, which is this lambda. Okay, I'm almost done. And also what's interesting with this kind of optimization, it has the possibility of suppressing unnecessary layers, because in that case actually the unit becomes linear and then everything collapses. Now, of course, there are challenges, because it's a much more difficult optimization problem. We need to allocate knots in an adaptive fashion, and we need to find a good trade-off between having more complex activation, but then what we can do, actually, we can get much shallower neural network, which are easier to control while preserving actually actually performance of the neural architecture. So anyway, I'm getting to the conclusion, and I like to call it the return of the spline. Okay, I'm a spline person, but okay, foundation of functional learning. So I told you that functional optimization in Banach space. So this is the key, and it's enabled by this very general representative theorem that I told you about. Now, in particular, we get back all the old stuff of classical learning, or all the tools which were producing kernel Hilbert space. But now, if we consider non-strictly convex Banach spaces and the ones that promote sparsity, actually, we get very interesting results. And so splines and machine learning is what I said. So traditional kernel method are very closely related to splines. Usually you put, you know, one knot or one basis function per data point. But the sparse variants seem to be much more interesting, because you can position your kernels in an adaptive fashion. And now also the thing is that, in fact, if we move to neural network architectures, actually they are also high-dimensional splines. And so I've proposed ways of functional optimization for streamlining neural architectures. For example, if we use our kind of algorithms, we have algorithms that can actually find the minimum number of neurons, because we have this sparsity promoting criteria, and also the possibility of freeform activation, which gives us deep splines. And for those interested, we also have like software now that implements those deep splines. And that gets me to the end and acknowledgement. So many people to thank here, also funding agencies. So I was covered by 2 ERC grants, and I'm very lucky to say that actually, based on the work I just proposed to you, I just got a new ERC grant to try to strengthen the math and results that I've presented to you. And finally, here are some primary references of what I've been talking about. In particular, this paper here, in Foundation of Computational Math, where you have this general representative theorem, and then you know, all kinds of algorithm for implementing the different variants that I've proposed in my presentation. And I'll stop here for questions.
Yeah, thank you very much for a great talk, Professor Unser. So now we have several questions in the Q&A box. So let me read out each question. So the first question is from Inzalian. The question is there any example of non-strictly convex Banach space that we could encounter in engineering applications?
Well, he told me it is answered in the rest of the talk. Thanks. But maybe just to, so thank you for also providing the question, the answer. So the ones that are super interesting is L1. And you remember, for example, Professor Sever is one of leading contributor also to the theory of compressed sensing. And this is all based on L1 optimization or this type of regularization functional. Now, the other one that's a little not used so much is L infinite. Okay, but this is used a little, for example, for filter design. But now there's also very recent evidence that neural networks are unstable. There's all this thing with deep fool, etc. And there's lots of activity now in neural networks in trying actually to enforce stability. For example, by enforcing bounds on Lipschitz. And Lipschitz is actually an infinite norm. Okay, and so this becomes super important. So in some sense, those are the two extremes. So L infinite is good for stability, and L1 is super good for having simple architectures.
Okay, thank you so much. Next, let's move to the next question from Sonoda-san. So does the main result suggest any pros and cons of ReLU activation function, for example, compared to like tangent hyperbolic or like ELU?
First of all, I mean, now that you know that ReLU neural networks produce continuous piecewise functions, which are splines, then you can use all the theory of splines, okay? And so you know that, with using continuous piecewise linear function, you can approximate anything as closely as you want. You have also bounds of approximation, etc. So you are in very familiar, safe ground, okay? So and then you also have those functional optimization arguments. So it's usually, you can look at the problem from various ends. So people have observed experimentally that really works well, but then you also have theoretical guarantees. The other thing is also, like, for example, if we use this M-norm type of regularization that I proposed in my talk with derivatives, actually you can show that those regularization, they're invariant to scaling. So in particular, let's say if you had a machine learning problem, and suddenly you change the scale, you multiply everyone by, let's say, 20. Okay, and you would need to retrain everything. And now if you were using regularization that is not scale invariant, you would probably find another solution. Now, if your regularization is scale invariant as splines, actually you find the same solution again. The algorithm doesn't care that everything was multiplied by 20. So that, for example, if we were using tangent hyperbolic, it would not be the case.
Okay, so thank you so much. And next question is from Lingu. What is the relation between today's material and the masked autoencoder? Oh, can you?
I don't know. You tell me. No. I've been working very hard. Because somehow, there's functional optimization. Okay, so I can say you have a very general theorem. Now, if somehow you can, identify a Banach space, then you can map it. But it's not easy. For example, the theorems I showed you about neural network, like the one by Savares and Novak and company. I mean, the one of Novak and company, it came out last year. Okay, because it's some kind of reverse engineering. So once you have something that works, and then okay, it's actually not so easy to show actually that there's a corresponding functional optimization problem, and I find it extremely elegant, actually, that you can do it like that, but it's not obvious at first sight. So we have a super weapon, which is the theorem, but now we need very smart people to fit problems into the theorem, okay? And sometimes it works, but sometimes not. So I don't know the connection with autoencoders.
Okay, thank you so much. Okay, next, let's move to the next question. The next question is from Hui Lee. I'm wondering that it would it be possible to compare the function space with bounded second order total variation norm and best of space in terms of the controlling a functional derivative?
Yes, actually, this is a super question. And in fact, we're trying to do so. And so there's some link. So in one it's easy. Okay, so actually the space, for example, the theorem that I presented for the shallow univariate networks and the regression splines. I mean those things actually they're very much related to Banach space. Or BV2. Bezos spaces and BV2. Up to some epsilons, they are the same spaces. Now, if you go to higher dimension, now you need this Radon transform, and so this brings us closer to the so-called Baron spaces, but not exactly. And actually, I mean, we have started working out some embeddings, and so they're really like relations with Bezos spaces. But it's a little vicious because you know those neural networks, they result in ridges, and so those ridges actually they don't decay. Huh? So I mean they're constant in some directions, and so the function spaces they're a little special. In particular, they need to include like polynomials. But then I mean you know exactly what you're doing because you have precise control of regularity, and you can tell what is Bezos regularity, and then you have all those results from approximation theory that can apply.
Okay, so thank you so much. Let's move to the final question from Inza. For my further interest, is there a link between the DS dual, the duality you used in the Banach space? I'm not sure whether I recall the name properly, and potential dual.
Yeah, so in some sense, yes, if we were in finite dimension, it would be the same. To me, it looks very similar because we're relying on duality, but it's not exactly the same. So because I mean this whole concept of duality in Banach space, so it's sort of functional analysis in Banach spaces. We're in infinite dimensions, and so this is really like tied to Banach spaces. As a functional dual is more general in some sense, but it's usually also done in simpler settings, okay, finite dimensional settings. But I would say, like from a mathematical point of view, it looks similar. The ideas are very similar, but it's not the same thing.
Okay, thank you very much. So now we are just in time. I would like to thank you again for a very nice talk, Professor Onzer. So let's thank the Professor Onzer. So I'm not sure whether we can do this.
Okay, well, thank you very much, everyone. And yeah. Okay, and if you want papers or pointers, you can also send me emails, and I will also make my presentation available. Okay, so thank you very much, everyone, and see you at the next presentations.
Thank you very much.